let's keep learning about surface integrals. So we have seen how to do surface integrals, meaning over a surface, there's a function. Every point in the surface has a value for some function f. And then what we did is integrate, add up, and quote unquote, add up all those values of f on some surface. That we came up with this formula. It's the values of the function in a parameterized, the surface parameterized in some parameter domain. And then times, we had to multiply to be able to do just a function, to do an integral just on the parameter space. We have to multiply by some conversion factor, and the conversion factor came up to be the length of the cross product of the tangent directions. These tangent directions, the length of this tangent vector, or the cross product of these two is what we call a normal vector. So it's the length of the normal vector to the surface. Okay. In the case that the surface is the graph of a function, it simplifies a little bit, and then you can just use this formula that it resembles the surface, the line integrals for the length of a graph of a curve, and other such formulas. Now, at the end of, towards the end of the last lecture, we're talking about, we're going to do now integrals of vector fields over surfaces. So there is a concept, just like we had an orientation for curves in the plane, that we were choosing to be a positive orientation if the curve was moving in the counterclockwise direction. There's going to be also a positive orientation for closed surfaces. So if you have a closed surface, the positive orientation is when the vectors point towards the outside. In this picture, it's not very clear, but what's happening is that these points are on the other side of the beam, and you see they're crossing through the beam. So this is the negative orientation, while this is the positive orientation of that normal vector. Either we will tell you, like, assume it's the positive orientation, so the vector, whatever the normal is, it's already what's going to be positive. Or if you have to come up with a positive orientation, you have to figure out what a normal vector is, and then just plot a couple of them just to see that they're pointing towards the outside of the surface. If the surface is not closed, there is no inside or outside, so this notion doesn't quite exist. But typically, we will choose one that is, if the surface tends to be grabbing some area of space, some region of space, the positive orientation will be when these vectors are pointing outwards. But as I said, if the surface is not a closed, completely closed surface, then there is no inside or outside. All right, so we came up with the formulas to do surface integrals of vector fields. And the surface integral of a vector field is the surface integral of the dot product of the vector field with the normal vector to the surface. The normal vector, the normal unit vector, as I said, is given by the cross product divided by its length. So this is a normal unit vector. And when we do an integral with respect to surface, this was the correction factor that we got. So this correction factor and that correction factor actually cancel out. And the integral just comes out to be this. The vector field evaluated at points on the surface, dot product with a normal vector. Not the unit normal vector, just the normal vector that's given by the cross product of the two. That's what's called a flux integral, and it measures sort of like the total flux of F across the surface. How much, how much is of this force, or how much of this flow is flowing out of the surface at any given time. All right. This formula is also resembling. It resembles also the formula that we got for the length. When we were integrating a vector field along a curve, we had this formula instead, which is the vector field evaluated at points on the curve, dot product with the tangent vector. So this is, in some sense, a similar formula to that one. So let's do some examples of how this is done. So we're going to find the flux of the vector field F across the surface given by that. We started setting this up last time. So let me give you more details on how to do that. This function is a paraboloid, but it's open up in the y direction. So this is a paraboloid. If this is up to 1, I can draw a circle here, and the paraboloid just goes like this. Okay? So we're talking about that paraboloid, and I want to integrate this vector field along this surface of the paraboloid. You see that as is, I'm just talking about the, it's hollow, and we're not considering the top of this sort of like drum or the top of this paraboloid. So it is not closed. So I am going to pick for a vector field, or for the normal to be pointing outwards to be the positively oriented one, but it could have been either way because it's not a closed surface. Okay, so how do we do this then? We're being asked to integrate. I want to do the integral over this surface. This is the surface, is this surface of F with respect to surface. So first, I want to parameterize this surface. So what I'm going to do is parameterize in U and V. I'm going to, let me just parameterize using the coordinates X and Z so that we follow what's in the picture instead of introducing more variables. I'm going to parameterize with respect to X and Z. And then the points are going to be there's X, and then there is Z, and the Y coordinate is given by X squared plus Z squared. Okay. Then I'm going to need the normal vector to this thing, so I need to find the partials or the tangent directions. Our X is 1, 2x, 0, and our Z in this case, in the direction of Z, that is 0, 2z, 1. Again, taking the derivative with respect to x, derivative with respect to z, so the derivative with respect to the first parameter, and derivative with respect to the second parameter. Now I can compute the cross product of the two. That will be I, j, k, and 1, 2x, 0, and 0, 2, z, 1. And when I do that, I get 2x minus 1, 2z. Is that vector pointing sort of towards the outside of this paraboloid or the inside? I can just evaluate this vector at one point, okay? And one point that I can use, for example, is at the parameters 0, 0, the parameterization at 0, 0, I can write it here. Where am I? At 0, 0, I'm at 0, 0, 0. So I'm talking about what's happening at this point. And when I evaluate this normal vector at that point, I get 0 minus 1, 0. First of all, this is a good check to see that this vector is normal. It has to be perpendicular to the tangent plane. I know what the tangent plane looks like here. The tangent plane is the YZ plane. And this vector is pointing at 0 minus 1, 0. It's pointing like this. So that looks exactly as it should, normal and pointing to the outside of the surface. If this surface was really the integral of a solid, if we had the top also in the surface, then this is definitely the positive orientation for this surface. Okay? Just imagine that we could think of like the solid could be the infinite solid that is sort of outside of the paraboloid. And in that case, the normal would be the one that is pointing to the inside of the paraboloid, right? So I have to, when we define the solid with the interior, then it's clear what's out and what's in. But right now, it's not entirely clear. So I'm going to pick this one, the one that is given, as the positive orientation, because they tell me, assume S is positively oriented as is. So these, I'm going to just keep this one. Okay. All right. So that is my 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 cross product. So now I can evaluate the integral. So what is going to be the integral of f ds over the surface is going to be the integral over the domain. Here the domain is the domain of the parameterization. Maybe we should have done that, right? We should have thought, what is the domain of my parameters? The x and the z can be where? All real numbers. Do we have a counteroffer? It would have been all the real numbers if this wasn't here. It is, what you see in the picture is the entire surface. It's not an infinite surface. If it was the infinite surface, probably the integral is, would you like to do improper integrals in 2 dimensions? Should we go into that? No. So this is a proper integral, and we're just going to integrate this piece. Since it is just this piece, I have to look at the parameters that will give me points just where I am. If you project this whole thing into the xz plane, which is where we're taking parameters from, we have the domain d for parameters is those points that are within the circle of radius 1, and it's in x and z. Okay? This is in the xz plane. So this is, maybe it would be clearer if I say that the domain are x and z values such that x squared plus z squared is less or equal to 1. That is my parameter. So let me, for a second, go back to the formula that I tried to follow. This is going to be this integral over the parameter domain. F evaluated at the parameterization of my surface, dot product, the cross product. So I need F evaluated at my parameterization. My parameterization, remember this is the parameterization over here. So when I evaluate F at this thing, maybe I can put it here so we see what it is. F evaluated at R at the parameterization is going to be 0. The y coordinate is x squared plus z squared, and the z coordinate is minus z, so I get minus z. Okay? So that I'm going to copy it here, 0, x squared plus z squared minus z. And the dot product, the rx, rz was 2x minus 1 to z. So I'm doing the dot product of the two, okay? If I dot both of them, f dot this cross product, I get the dot is 0 times 2x, that's 0, plus minus 1 times x squared plus z squared, plus minus z times 2z, so minus 2z squared. So in total, this is minus x squared minus 3z squared. So this is the integral of minus x squared minus 3z squared dA in area. So we are integrating that over d again is a circle, a filled-in circle of radius 1. That's my my domain for that double integral. Before I do that double integral, any questions about the setup of this vector field integral? Yeah, so this over here is f of rxz dot with rx cross product rz. So I'm doing this coordinate times this coordinate, 0, this coordinate times this coordinate, this, and this coordinate times this coordinate is minus 2z squared.
But Rx and RZ are the partial derivatives, right?
Yes, but we had already computed those. So I already know what the cross product of the two. I computed the partial derivatives. Those are the partial derivative directions. And I computed the cross product already, so I know it's this vector. So that's the vector I'm using here to dot with this to get this. Okay, so do I have another slide here? Yes, so let me do the integral over d of minus x squared minus 3z squared d area. I'm going to try to be as clever as possible by doing the following. So what I'm going to do is I'm going to break this as an integral in d, well, first with a minus there, of x squared d area, and minus 3 an integral in d of z squared d area. So what happens is in the unit disk, integrating x squared on the unit disk of radius 1 or integrating z squared on the unit disk of radius 1 is actually the same function, okay? So integrating in the disk x squared with respect to area is actually the same as the integral in the disk of z squared d area, where the disk is just x squared plus z squared less or equal to 1. So by symmetry, those two things are the same. And I can just compute one of them, okay? So I would have to compute what that is. And for that, I'm not going to do it here, but this, I would use polar. I would use, not polar, but polar coordinates to parameterize the circle and do that integral. And it turns out that this integral is just pi over 4. So this integral is also pi over 4. And then the answer will be minus pi over 4 minus 3 pi over 4. So I get minus 4 pi over 4, so minus pi. I could do without the polar coordinates. I have to parameterize a circle in Cartesian coordinates. So it would be something like from minus 1 to 1, and then the y would go from minus the square root of 1 minus x squared to the square root of 1 minus x squared. It's more complicated to do it in Cartesian coordinates, so it can be done. Yes?
How can the surface area of that object be negative?
It is not a surface area, right? We were integrating. We are integrating, first of all, in here we're integrating what is the flux of this vector field in the entire surface. This vector field at any given point, it has a direction, and we're sort of like adding up all the possible contributions just to see how much is flowing in one direction, how much maybe is coming in from another direction, and computing the entire flux. And then if you mean in here, it is not a surface area. If it was just a surface area, if it was just the area of the disk of radius 1, it would be pi. But I am integrating the value of the coordinate x squared in the entire circle. So I'm integrating a function, the value of a function in the entire circle, and that is no longer just the area of the circle. Okay? For example, if I was integrating, this is the function x squared. If I was integrating the function x, then the function x has as many negative values when x is negative as it has positive values when x is positive, and the integral would have to be 0 by symmetry. Okay? So it's not just a surface area, it's not just an area, it's the area of a function, just like this function, this over here, is not the surface area of the paraboloid. It is, we're integrating how much is the total flux of a vector field. Well, I think the one way to interpret it is this, like I'm computing all the, I think if it was just fluid, like consider there is some volume inside it, and how much fluid is escaping the paraboloid per second, essentially. Okay, so if time was this with respect to, if this, it's constant equal to minus pi. The flux is constant equal to minus pi in the way this is set up. So here the flow is, it's not constant, it depends on the point, but there is some constant flow, and at every point it's constant equal to the position of the point, but there is some flowing, and in this case I guess it's minus pi, it's saying that there is more flow towards the inside than there is towards the outside. Okay? All right, let's do some other example. In here, I'm going to set up an integral of a vector field, but in this vector field, the vector field itself is a curl of f, just so we get some practice on computing a curl. Now, what is this surface to begin with? What's the surface? Let me start with, so this is x, y, and z. If I just plot z equals x squared plus y squared up to 9, okay, so there's going to be something like this, and then a paraboloid, again like this. But they're telling me that I'm only going from 1 up to 9, so I'm going to cut it starting from here up to here, okay? Like this. So it is this surface in yellow is the surface, and there is one more condition that y has to be positive. So it's not even this. Let me do one more cut here. Y has to be positive, so it's this half of the paraboloid. Okay, like that, and just the surface of the paraboloid. Okay, so I want to try to integrate that. One question is already just parameterizing that thing. We're going to have to figure out what that is. There is also the question of what is the parameter space. You can see that the parameter space is going to start with at 1, and it's going to go all the way up to 3. So the parameter space is going to be something like this. It's an annulus, because I have to figure out that it has to go from x squared plus y squared. It has to go from x squared plus y squared equals 1 up to x squared plus y squared equals 9. So it's an annulus, and with y positive, it's something like this. Okay, so that's going to be the parameter space once we've passed it to an integral in the domain of the parameters. So let me first figure out what is the curl of this beast. So let's start with let's start with the curl. So f is z squared x squared y squared. And I'm going to compute the curl. The curl, remember, that is the gradient cross f. This is called the curl of f. Okay, so that is given by I, j, k, and then derivative with respect to x, derivative with respect to y, derivative with respect to z, which is the gradient, and then f, which is z squared, x squared, y squared. That is what the curl is going to be. And that is going to be, so the coordinating I will be the derivative with respect to y of y squared minus the derivative with respect to z of x squared, etc. So without doing all those derivatives, this turns out to be 2y, 2z, 2x. Is that positively oriented? is that vector field. Well, this is just the kernel of f, so that doesn't matter. What we need is going to be the normal vector to the surface, which is what I'm going to calculate next. So that is the kernel. Any questions about the kernel? Are you saying like, why is this component non-zero? So this component right here comes from doing this determinant, right? Remember that to compute this cross product, this is going to be I times the derivative with respect to y, derivative with respect to z, x squared, y squared. So that's going to be I times the derivative with respect to y of y squared minus the derivative with respect to z of x squared. The derivative with respect to y is 2y, but the derivative with respect to z of x squared is 0. So I get 2y. So that is why I get that component is 2y. Okay? So you have to do all these three 2 by 2 determinants to compute each coordinate. There's this long formula that I honestly don't remember for the kernel, which is this like difference of derivatives. I think that's super confusing. So I just remember to write it as the cross product of the gradient and the vector field. Okay, so we have the curl. Now I need the normal vector, because remember that this is going to be a cross product with the normal vector. So dot product with the normal vector. So now I need to parameterize this domain. So the domain is going to be points x, y, such that they are between x squared plus y squared, and y is bigger or equal to 0. And the parameterization of the surface for every x and y, what I get as a parameterization is, well, it's x, y, x squared plus y squared. Okay? I can compute the derivative with respect to x is 1, 0, 2x. The derivative with respect to y, that's 0, 1, 2y. And now the cross product, that's going to be I, j, k, 1, 0, 2x, 0, 1, 2y. And that is going to be minus 2x, then minus 2y, and 1. It is minus 2y because in the j coordinate I have to do, let me do, this is I times something minus j. Remember that the expression is plus k times, there's an alternating sign, right, on those determinants. So in j, I have 1 times 2y minus 0, so it's 2y, but I have to flip the sign because of the expression, the alternating signs of the minors.
Wait, why is I negative?
And I, for I, the determinant here is 0 times 2y, which is 0, minus 1 times 2x. So it has to be minus 2x. Okay? Now, here, this vector is the normal. And if I apply it somewhere, for example, when, let's see what this vector looks like at one of the points on the domain, a pointed domain, for example, when x is 1 and y is 0 is in the domain, y is bigger or equal to 0 there. So for example, at 1, 0, I get minus 2, 0, 1. As a normal vector. Okay, let's look what that looks like. Where is 1, 0? 1, 0 is this point right here. Okay, and at that point right there, that point right here corresponds to this point right here, and the vector is minus 2, 0, 1. So it points like this towards the inside, what I'm perceiving as the inside of that surface, right? But who is to tell me what's the inside and what's the outside of something that is not closed? So that's why I'm saying assume that it is positively oriented. Assume that whatever normal vector you come up with, that's the positive orientation. Okay, so not to complicate things. Just because, as I said, this could be, you could imagine that this is sort of like a solid like this, and then that would be negatively oriented. Or maybe the solid is something like this, like it just continues on the other side, right? And then it is positively oriented. So we don't know what the total solid is going to be. So we don't have a way to tell positive versus negative oriented yet, because it's not a complete solid. It's not a closed solid. So let's just take that as our normal vector, okay? Or this one. That's going to be our normal. So now we are going to, we're ready to rumble, because now we have, so now the curl of F is this cross product, which we identified as 2y, 2z, 2x, but I have to evaluate it at my parameterization, okay? So this is some step where I have to apply the parameterization that I have of my surface, and remember that the parameterization itself was x, it was in x and y in this problem, and the parameterization was x, y, x squared plus y squared. So now I have to plug in this into this, and then what I'm going to get is 2y, the y is y, so I get 2y, 2z, but here the z value is this, so I get x squared plus y squared, and 2x, the x coordinate is the x coordinate, so I just get 2x. Okay? And then I'm going to have to do the dot product with the normal vector. So now what is the curl of F evaluated at here, dot the Rx, not in absolute value, but just the actual vector that we got for cross product. So that's going to be 2y, 2x squared plus y squared, 2x, dot, whatever we got before, which was, it was here, minus 2x minus 2y, 1. So that is, all in all, I get minus 4xy minus 4y x squared plus y squared plus 2x. And that is the function I have to integrate in my domain. Okay, so what do I have? I have that this integral over S of the curl of F ds turns out to be the integral over this domain that was some sort of annulus of minus 4xy minus 4y x squared plus y squared plus 2x in area, where again the domain was x and y between with the radius between 1 and 9, and y is positive. Okay? They told me to just set it up, so I'm going to leave it here as set up. Now, if I actually want to integrate this, I would try to use probably, I would do polar coordinates, okay? So can you tell me what is d in polar? So the radius is between 1 and 3, right? You said it right. The radius square was between 1 and 9. but that might as well say that the radius is between 1 and 3. And theta, so that's a good guess, but we start counting here, and we move that way. So this is 0. So it's not, if 0 is not here. So you said you were trying to say from minus pi over 2 to pi over 2, but this is actually 0. We start here, the theta, so it's going from 0 to pi. So it's half a circle. So it is going from 0 to pi. And then you can do the integral in polar coordinates. You have to change x is r cosine theta, and y is r sine theta, and x squared plus y squared is r squared, dot, 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 and you can transform that into polar and solve it that way. Why do I keep making more complicated? So when we are integrating, we're integrating, let me say I'm integrating, for example, over a surface, I'm integrating some vector field G ds, okay? The formula is going to be an integral over the domain of values, okay, for my parameterization. G evaluated at the parameterization, dot product with the cross product of the partial derivatives, dA. So that is the formula. So what this means is that whatever was the vector field, I still have to evaluate it at the parameterization I got of my surface. In here, just not to introduce u and v, I call these also x and y, but it makes it a little bit confusing, the transformation from here to here, that I'm evaluating this vector field at this parameterization. At the y coordinate, I'm looking at this y coordinate and plugging this y coordinate, but this z coordinate, I'm looking at this z coordinate here and plugging it in here. So what I'm following really is this formula to be able to compute, to set up my integral and following that formula, which is the formula we came up with when I was doing the a surface integral of a vector field.
So did we skip the U and the V?
I didn't call them u and v, I called them x and y because I just wanted to know, I wanted to keep track of in the parameterization. Here I parameterized the annulus, and that annulus, since the annulus was here in the xy plane, you can change the parameters to be u and v's in here, but since it is in x and y, I just used x and y again for the parameters for these parameterization. So this is the parameterization that in the formula, if we go all the way back to the formula, these u and v's are supposed to be the parameters that are parameterizing the surface, which in here I did. Again, I parameterized the surface, but I was just using x and y for my parameters.
So what was the first step that we went into U and V? Like from the very beginning, or like when you did the D?
In here, I have f, and I'm just computing the curl of f, so there's no u and v's.
Yeah.
Here is where sort of like the u and v appear. These are the parameters I'm using to parameterize the domain of the parameterization, which is this annulus. So these are what in the general formula sometimes are called u and v.